All right, so let's begin sections 2.3 through 2.5. In this video, we are going to look at what I'll call shortcuts to taking derivatives. This is going to save us a lot of time in the process. We saw the limit definition in the last video and saw how long and tedious that can be. So hopefully after this video, you'll learn some of the shortcuts and be able to save a little bit of time. So probably the most basic rules when it comes to derivatives are the power rule and what we'll call the constant rule. When you want to take the derivative of an x raised to a power of n, all you have to do is take the power n, the exponent n, bring it to the front, which you get here, and then you subtract 1 from the original power. There's a special case that if you have the derivative of just an x to the first, that's going to always become 1. That's kind of similar to, as we saw in the last video, that when you did the derivative of a linear function, you only got the slope. Well, since the understood number in front of the x is 1, that is where that number is coming from. If the derivative of 2x was there, you would say the answer is 2. And if you're asked to take the derivative of a constant, you will say that that answer is always 0. So let's look at some examples here. Find the derivative of the following. You have 5 to the 60th power. Well, since there aren't any x's involved, and that's just one large number, that's considered a constant. Therefore, your derivative is 0. Now, what happens when you do have x's? What if you have something like 7/4 x squared minus 3x plus 12? Well, what the power rule says you're allowed to do is you're going to take the 2, you're going to multiply it by the 7/4, so that would be 2 times 7/4 x, subtract 1 from the power, which makes it the first. The negative 3x, as we saw a minute ago, just becomes negative 3, and the 12 just goes to 0 because it is a constant. If you simplify the 2 times 7/4, this would end up being 7/2 x minus 3. That is a lot nicer than having to go through that long limit definition in the process. All right, so what if you have a couple of special cases? What if negatives and fractions are involved? What about something like 2t to the negative 3/4? If you want to find the derivative of this, so g prime of t, this would be equal to, so negative 3/4 times 2, so negative 3/4 times 2, t, and if you subtract 1 from the power, negative 3/4 minus 1 is negative 7/4, and if you simplify the two constants, negative 3/4 times 2 would give you a negative 3/2 t to the negative 7/4. So just make sure you're comfortable subtracting 1 from fractions. We'll see a lot of that, especially when we get to radicals a little bit more later. When you have something like 5 over r cubed, first time seeing a letter in the bottom, we haven't talked about how to deal with that explicitly yet. So for now, what I'll suggest you do is you bring that r to the top, which can be written as the same thing as 5 times r to the negative third, and then you can just apply your power rule. You can bring the negative 3 to the front, a little easier this time. Negative 3 times 5 is negative 15 r, and if you subtract 1 from the power, that becomes the negative 4th. That is your derivative. All right. Now we get into, like I said, every problem will show you a little bit different idea every time. So what I want to see here is what is the derivative of x squared plus 2x minus 5 over the square root of x? Well, first thing to remember is that when you have a square root of x, remember from algebra that that is the same thing as x raised to the 1/2 power. So that bottom term you can change to a 1/2 power, but then you've got to divide each and every term by that. So if I were to rewrite this, I could write this as x squared over x to the 1/2 plus 2x over x to the 1/2 minus 5 over x to the 1/2. And you can simplify each of these in a more individual manner. So x squared over x to the 1/2 is going to be x to the 3/2 plus 2. X over x to the 1/2 is x to the 1/2. And since the last one doesn't simplify, I'll just bring that power to the top and make it a negative exponent instead. So now you can apply the power rule of that new term. So if you do the power rule of all three pieces, you should get 3/2 x to the 1/2 plus half of 2 is just 1, so that goes away. You can put the 1 there if you want to, but it really just becomes x to the negative 1/2, and then you get a plus 5/2 x to the negative 3/2. Once again, that 1 is understood, but it is there if you would like to write it down. So that is another way that you can rewrite an ugly fraction into a power rule problem. All right, so then we get to our first two special rules. What happens when two functions are being multiplied or two functions are being divided and you need to take the derivative of those? So if you have the derivative of f of x times g of x, that's the same thing as f of x times the derivative of g of x plus g of x times the derivative of f of x. So one thing you'll see me write a lot today is instead of this long definition, I write a lot of fg prime plus gf prime, just a little bit more shorthand notation so that I can express the product rule a little quicker for y'all. I do the same thing when it comes to the quotient rule. So the quotient rule says if you're taking the derivative of two functions being divided, f of x over g of x, you would do g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared, or as I will probably shorthand it, gf prime minus fg prime over g squared. So we're going to look at a few examples of these rules. We'll start off with a couple of product rules, and then we will move into a couple of quotient rule examples for you. So first example, find the derivative of 5x squared minus 2 times x cubed plus 3x. So I'm going to show you two different ways this can be done. On this first one, you could expand this, and I'll do that on the next one, but just to kind of show you how the product rule works, if I let this be the two functions, we'll say f and g, the product rule says that since they are being multiplied together, their derivative can be found by doing f times g prime plus g times f prime. So by doing that, it says that I can take the f function, which is 5x squared minus 2, multiply it by the derivative of g, which is 3x squared plus 3. Then you can add to that your g function, which is x cubed plus 3x, times the derivative of your f function, which is 10x. Now you will need to multiply all this out to simplify it into one function, so let's do that. The first two terms you can FOIL, which will give you a 15x to the fourth, a plus 15x squared, a minus 6x squared, and a minus 6. And then on the last one, if you just distribute that 10 through, that is a 10x to the fourth plus 30x squared. So 15x to the fourth plus 10x to the fourth is going to give us 25x to the fourth. Then you combine all of your x squareds. Let's see, that's 45 minus 6 is a 39x squared. And then the lonely minus 6 on the end. So that is an example of where you can use the product rule to find the derivative. Now on the next one, I'm actually going to show you a different way that this same problem could have been done. Instead of using the product rule, some of y'all may be encouraged to do it this way. So what about something like this? You have find the derivative of 1 over y squared minus 3 over y to the fourth times y plus 5y cubed. All right, so once again, you can work this one just like the previous example I just did, or maybe here's a different way. Instead of doing the product rule, what if you just want to instead go ahead and FOIL this? So why don't we just FOIL this and see what happens? That would end up saying that f of y is equal to 1 over y squared times y, so that's your first. Your outer is 1 over y squared times 5y cubed minus, your inner is negative 3 over y to the fourth times y, and your last is 3 over y to the fourth times 5y cubed. By simplifying all four of those products, you should get 1 over y plus 5y minus 3 over y cubed minus 3, sorry, not minus 3, sorry. 3 times 5 is 15, not 3. Let me get rid of the 3. There we go. 3 times 5 is 15 over y. Now I also see the first and the last term go together, so that is negative 14 over y plus 5y minus 3 over y cubed. And instead of having to do the product rule now, I had to do a little bit of algebra, but now I can rewrite this into a power rule. So this is the same thing as negative 14y to the negative 1. The 5y is already in the right format. And then minus 3y to the negative third. So after all that algebra, you can now say that f prime of y is equal to 14y to the negative 2 plus 5 plus 9y to the negative fourth. And you're done. It's really up to preference whether you'd rather do the algebra up front and then the derivative, or whether you would rather do the derivative and then the algebra when it comes to the product. So that's up to you. Now just keep in mind that there are times that this rule doesn't work. There will be a couple of special product rules we see later that you will have to actually know the rule, especially in the next section. All right, let's look at a quotient rule example. What about find the derivative of 1 plus 2x over 3 minus 4x. Now in this example, you have a function on top that I'll call f and a function on the bottom that I'll call g. So the quotient rule says that since they're being divided, you can find the derivative of this by doing gf prime minus fg prime all over g squared. So when I go to apply the quotient rule here, this would be g is 3 minus 4x times the derivative of f, which is 2, minus f times the derivative of g, which is negative 4, all over g squared. And the good thing about these quotient rules is the one thing I'm looking for you to do is to simplify the numerator, so go ahead and do that. That should end up being 6 minus 8x minus a negative 4 minus 8x all over 3 minus 4x all squared. Distribute that negative through, and it's 6 minus 8x plus 4 plus 8x all over 3 minus 4x all squared. And really the big thing we notice here is that the 8x's actually cancel each other, so I'll take care of that. And this gives you 6 plus 4, which is 10 on top, divided by a 3 minus 4x all squared. And that is an example of the quotient rule. Unlike the product rule where you can kind of sometimes shorthand it, I kind of showed you how you can get around it, the quotient rule, there is no way around it. You will have to know how to do the quotient rule when two functions are being divided by each other. Let's look at a second example here. All right, so we're going to take what is the derivative of the square root of x over 2 plus x. All right, so once again, one thing I'm going to do up front to take care of this is that we don't like the square root form. So I'm going to write this as x to the 1/2 over 2 plus x. That way it's already in the right format for when I do start to do my quotient rule here. So remember, we're going to let f be the top and g be the bottom. So the quotient rule says you're going to do gf prime minus fg prime over g squared. All right, so in this case, when we go to apply the quotient rule here, y prime is equal to 2 plus x, that's g, times the derivative of f, which is the power rule, so 1/2 x to the negative 1/2, minus f, which is x to the 1/2, times g, the derivative of g, which is just 1, divided by g squared. All right, so if I clean up the numerator again, you distribute that term through, you should get an x to the negative 1/2 plus a 1/2 x to the positive 1/2 minus that x to the 1/2 on the right, all over 2 plus x all squared. And you can put together these two x to the 1/2 terms, and you have an x to the negative 1/2 minus a 1/2 x to the 1/2 all over 2 plus x squared. And that is the derivative using your quotient rule. All right, so kind of going back to a topic we covered in previous sections, the equations of tangent lines. So we talked about the long limit definition way of doing tangent lines. So I will show you a faster way now that we know shortcuts to derivatives in order to do that. And then we'll also talk about normal lines, which is just a line that's perpendicular to the tangent line. If you don't remember how to do perpendicular, that's okay. I'm going to show you how to do that on the next slide when we do our example. So here's my first one. Find the equation of the tangent line and the normal line to the curve at the given point 1, 3 if y is 2x cubed minus x squared plus 2. So now that we know shortcuts to derivatives, here is my suggestion to finding the tangent line. Step number 1, we used the limit to find a derivative in the last video. Now we know shortcuts. So let's find the derivative of this function. That would be 6x squared minus 2x. We normally plugged a into our limit. Well, remember, what is a now? A is the x value of your point. So on part 2, to find the slope of a tangent line, you need to plug your x value into the derivative, which is going to be 1. So that would be 6 times 1 squared minus 2 times 1, which does simplify into 4. Once you get the slope and once you have the point, which I gave to you already, you can write the equation of your line. It is y minus 3 equals 4 times x minus 1, which is y minus 3 equals 4x minus 4. So y is 4x minus 1. That is the equation of your tangent line. A lot quicker and a lot more straightforward than what it was in the last sections. But now we get to the normal line. So if you want to find a normal line slope, that's the only thing we need different. We already have the point. A normal line slope is going to be the opposite reciprocal. So that means that since our slope of the tangent line was 4, to do the reciprocal, you flip it over. And when I say opposite, I mean change the sign. So instead of being 4, it would be negative 1/4. You're going to use negative 1/4 and the original point to write another equation of a line. This would now be y minus 3 equals negative 1/4 times x minus 1. So y minus 3 equals negative 1/4 x plus 1/4. And if you add 3 to both sides, you might have to do some common denominators here. 1/4 plus 3 is going to give you 13/4. And that is the equation of the normal line to the curve at the point 1, 3. Then we get into a special kind of tangent line. So what if you're looking for a particular point that makes tangent lines, let's say, horizontal? This is going to play a big role in graphing that we do in chapter 3, but to kind of show you what I mean now, can you find the points on the curve where the tangent line is horizontal for the following function? So before I get into the function, well, what does it mean for tangent line to be horizontal? Horizontal, from algebra, says that you need to have a slope of 0. Well, if you want to know what points make the slope 0, and since tangent lines come from derivatives, you're asking yourself, where does the derivative equal 0 at? So let's find the derivative. Y prime is 6x squared plus 6x minus 12. That's from the power rule, and you're going to set that equal to 0. All of those terms share a 6 in common, so I'll factor that out. X squared plus x minus 2 equals 0. Factor that quadratic. It should factor into x plus 2 times x minus 1. And then from algebra, you're going to set all of those equal to 0. Now, setting the 6 equal to 0 doesn't do anything, so don't worry about that. Instead, I'm going to do the x plus 2 is 0. And the x minus 1 is 0. And solving both of those equations separately give you two different x values, negative 2 and positive 1. Since it wants the points on your homework, you're going to have to also find the y values of those x's. So just plug these x's back into the original function. That way you can get their y's. So let's find y of -2 first. That'll be 2 times -2 cubed plus 3 times -2 squared minus 12 times -2 plus 1, which is going to end up equaling, let's see, quick little mental math here. There's that's going to end up being 21. And if you plug 1 into this, so it's 2 times 1 cubed plus 3 times 1 squared minus 12 times 1 plus 1 should give us, looks like, -6. That means your 2 points where horizontal tangents occur are going to be -2, 21, and 1, -6. But remember, that comes from because the slope of the tangent line being 0 means that it's horizontal, so we took the derivative and we set it equal to 0. All right, so that ends section 2.3. Let's move into section 2.4, which is going to be all about trig functions. So we're going to look through some trig stuff here with you. First thing you're going to notice is that there are 6 trig functions that we know of: sine, cosine, tangent, cosecant, secant, and cotangent. To find the derivatives of these, this is going to be the chart that you need to learn. You need to know all 6 of these derivatives to be able to apply them to different problems. So let's run through these from left to right. The derivative of sine is cosine, and the derivative of cosine is negative sine. These 2 are probably the most popular, so that's the 2 that I definitely would focus on, but the other 4 are important as well. The derivative of tangent is secant squared. The derivative of cosecant is negative cosecant cotangent. The derivative of secant is secant tangent, and the derivative of cotangent is negative cosecant squared. So if you need to pause the video to write those down, I would recommend that. These top 2 are very important going forward, but you need to know all 6 for your assignments. So let's start with this one. Find the derivative of tangent of x 2 different ways. So what do I mean by 2 different ways? Well, step number 1, or the first way, is by memorization. If you learn that chart, you will go back and see it, you will see that the derivative of tangent is secant squared. If you choose to memorize, which I recommend, that's the fastest way to do it. But there is another way. We could say that tangent of x, from our identities in trig, tangent of x is the same thing as sine of x over cosine of x, and to take the derivative of that, you could use your quotient rule that we covered in the last section to do that. So remember, quotient rule says that you can do gf prime minus fg prime all over g squared. So if I apply the quotient rule to sine divided by cosine, I could say that this is cosine of x, excuse me, times cosine of x, because that's the derivative of sine, minus sine of x, times the derivative of cosine is negative sine, all divided by cosine squared. Now if you simplify the top, that comes out to be cosine squared of x plus sine squared of x over cosine squared of x. And then from the most famous identity in trig, cosine squared plus sine squared is 1. So that's 1 over cosine squared. And back in the trig review section, we talked about that 1 over cosine is secant. Well, very similar, 1 over cosine squared is secant squared. And as you can see, we got the exact same derivative on both of them. So I prefer you to memorize them. That'll be a lot easier, I think, for stuff you have to learn later. But if you want to do it the long way, it's right there for you. All right, so what about, so learning the 6 rules is just learning the 6 rules. It's being able to apply them in different spots. So for example, what if you want to take the derivative of x squared times the cosine of x? You'll notice that you have this x squared term being multiplied by the cosine term. And when you hear the word multiplied, that screams product rule, where I can let the first term be f and the second term be g. So the product rule says you can do fg prime plus gf prime. So let's see what happens when we do that. F prime of x is going to equal x squared times the derivative of g, which is going to be negative sine of x, plus g, which is cosine x, times the derivative of f, which is 2x. Multiplying this stuff together, not much happens. Negative x squared sine of x plus 2x cosine of x. That's the most it simplifies, and that's it. The trig derivatives overall are not that difficult to handle. It's just being able to combine them with different rules. That way you're not caught off guard when that shows up. But very good. What about one where you have to do quotient rules? So the one earlier with tangent by itself, you could have just learned the rules. But on one like this, you will have to be able to apply the quotient rule. So what is the derivative of x over 2 minus tangent of x? So the top function will be our f, and the bottom function will be our g. And I'm going to keep writing this down every time today so we don't forget it. The quotient rule is going to be equal to gf prime minus fg prime over g squared. So y prime can be found as being your g, which is 2 minus tangent of x, times f prime, which is just 1, minus f, which is x. The derivative of g, the derivative of 2 is 0. The derivative of tangent is secant squared, but the negative in front means you have to write this as negative secant squared all over g squared. Clean up your numerator like we did in the last section. This would be 2 minus tangent of x plus x secant squared of x all over 2 minus tangent of x all squared. That's the most it's going to simplify, and I'm happy if you get right there. So kind of like the product rule, the quotient rule wasn't much more difficult. You just have to be able to know your rules and be able to apply them using trig. All right. Tangent line. So we did tangent lines in the last section. We're going to do tangent lines in this section as well. So that means we're going to find the equation of the tangent line to the curve at pi over 3, 2 for the function y equals secant of x. All right, so kind of from earlier, step number 1, find your derivative. So from your chart in this section, the derivative of secant x is secant x tangent of x. Step number 2, to find the slope of the tangent line, you need to plug your x value, which in this case is pi over 3, and you need to evaluate the slope of the tangent line. So that's going to end up being the secant of pi over 3 times the tangent of pi over 3. So hopefully you've been learning your trig values, because from here on out, I'm going to kind of give you I'm going to tell you what the values are, and your job is to know where they're coming from. Secant of pi over 3 is 2. Tangent of pi over 3 is root 3. So that is your slope of your tangent line. Now you can use the point and the slope to write your line. That would be y minus 2 equals 2 square roots of 3 times x minus pi over 3. All right, distribute your slope through. This will be y minus 2 equals 2 square roots of 3 times x minus 2 square roots of 3 times pi over 3. Then you add the 2 over, which is not going to be very nice, so don't make it harder. Just leave it alone. 2 root 3x minus 2 root 3 pi over 3, and then plus an additional 2. These last two constants don't go together very nicely. That's fine. Just leave them separately. Sometimes our tangent lines will not be pretty. It's more about can you do them exactly than whether or not they're pretty or not. So very good. That's the equation of your tangent line. All right, so horizontal tangent. For what values of x does the graph have a horizontal tangent? So remember from about a few minutes ago, when you're trying to figure out the value for what values of x is the graph of a horizontal tangent, you want to take the derivative of your function and ask yourself, where does that equal 0? So if I find the derivative, f prime of x is going to equal 1 plus 2, and the derivative of sine is cosine. We're going to set that equal to 0. Like we did in the trig review section, you need to get the cosine by itself. So if I subtract 1 from both sides, you get 2 cosine of x equals -1. And then dividing both sides by 2, you get cosine of x equals -1/2. And then you got to ask yourself, where is cosine -1/2? So to kind of give you a little bit of a boost, remember, where is cosine negative? Well, that's in the S and the T quadrant, so there should be an answer in quadrant 2 and quadrant 3. And by doing some trig review, you should find the answers to be 2 pi over 3 and 4 pi over 3. That is where the x values of horizontal tangent. All right, and then one last little thing here at the end is let's just look through how to do higher order derivatives. So something about trig derivatives is that you'll notice that they do repeat themselves and they become periodic. So an example to kind of show you that is, how do you find something like the 73rd derivative of a sine function? All right, so what I want you to see here is, if I start with the original sine function, so let's say in this case y is sine, then if you start finding derivatives, see if you can notice the pattern. Sine's derivative becomes cosine. Cosine's derivative becomes negative sine. The derivative of negative sine is negative cosine, all the way until you get to the fourth derivative, and ta-da! You notice that the original function and the fourth derivative are exactly the same thing. That means that every 4 derivatives, the sine derivative repeats itself. So what I would recommend you do is not find 73 derivatives by hand, but instead divide it by 4 and see if you can figure out how to do that. 4 goes into 7 one time, so back to 3rd grade math for a second. 4 goes into 33 8 times, so that's 32, and here's the big thing. The remainder of 1. That means that you would go through 18 cycles of these 4 repeating, and that didn't do anything. But that 1 remainder is actually how far you need to go into this. So the remainder 1 tells you how many actual derivatives you need to find. So that answer is 1. The 73rd derivative of a sine function is just going to be cosine. All right, so that now leads us into the last section. So we're going to look at the last section for this video. We're going to look at the last new rule for now, and which is called the chain rule. All right. The chain rule is a way that we can find derivatives of functions that you don't really want to have to be able to expand, because expanding would take a lot longer than really necessary. It also helps us deal with what we saw back in the algebra review, which is composition functions. So this is a couple big charts here. Don't write all of this down. Once I finish going over it, if you want to pause and write down what I box in, that's what I would recommend you do. But essentially what the chain rule, like I said, is a way for you to deal with how do you find the derivative of composition functions. Those can be either polynomial. We'll see some trig functions today as well. I don't actually use these 2 definitions at the top. The 2 that I prefer you to write down would be these 2. So if you want to pause the video right now, write these down and then listen to my explanation, that's fine. Essentially what this says is that if you have a function which we define as u being equal to g of x, if that function g of x is being raised to a power of n, you can take that power of n, like the power rule, and bring it to the front. You don't mess with the g of x. You still drop the power down by 1. And the extra piece is that the chain rule says you have to take the derivative of the inside function. So whatever that g of x is right there, you leave it alone on the first step, but you take the derivative of that, and that's what comes out to the side. Then you can simplify a little bit from here and there, and then you can see what you get. All right, so let's look at a few examples of the chain rule. So here's kind of a prototypical example of where it would be useful. What is the derivative of 5x to the 6 plus 2x cubed all raised to the 4th? So instead of having to expand all of this, excuse me, is you can apply our chain rule. So let me kind of go step by step and show you what the chain rule is in this case. So capital F prime of x is going to equal. The chain rule says you take the power 4 and you bring it to the front. You do not mess with the inside. That's kind of like your g of x term. You subtract 1 from the power, which is 3. And then the chain rule says if this is your g of x, the inside part, take the derivative of that and bring it out to the side. 5x to the 6 becomes 30x to the 5th. 2x cubed becomes 6x squared. And the only thing you have to do now is take this 4 and apply it to the two terms you got out. That way everything looks a little bit nicer. So you're left with 5x to the 6 plus 2x cubed, all raised to the third, times, let's see, that would give us 120x to the 5th plus 24x squared. That is a lot nicer than having to expand all of that out by a bunch of terms. So that is essentially what the chain rule is. It's got a few other kinks we're going to go through here in a second, but that's the basic idea of it. All right. Another spot chain rules use a lot of is when you have square roots of something other than x. So we did square root of x in the power rule section. What if you want to do a square root of something other than x, let's say like 6x minus 7? Your first step's actually no different. You're going to have to rewrite this as a power of 1/2. So I'll rewrite this as 6x minus 7 all raised to the 1/2 power. All right, and what the chain rule says is that if you bring the 1/2 to the front, that's your power, you leave the inside alone, which is g of x, subtract your power by 1 to the negative 1/2, and then you multiply by the derivative of the inside, which using power rule is just 6. All right, the only thing you can do from here is if you take half of 6, that's a pretty easy computation, that would be 3 times 6x minus 7 to the negative 1/2. And that's a way that you can take the derivatives of square roots of something other than just an x. All right, now let's start combining rules. So these next few problems are going to take a little bit longer to do, so here we go. What is the derivative of, let's say, an x times a sine of pi x? Not only is this going to combine us into the product rule that we've seen before, but it goes into our last little part of chain rule we haven't gone over yet. So first thing you'll notice is that you have two functions being multiplied, an x and a sine of pi x. So like I did a couple sections ago and in the last section, if I let the first term be f and the second term be g, since they're being multiplied, the product rule says you can do the fg prime plus gf prime. Now here comes the kicker. When you go to find the derivative of this function, you would take f, which is x, and here's your next chain rule part. Anytime you have a trig function of an angle and the angle is something other than x, like pi x, that means you have to do the chain rule technically. So here's how the chain rule works in trig. You take the derivative of the trig function, which is cosine pi x. Your g of x term is actually the angle, so you don't touch the angle in this case. And then you have to multiply it by the derivative of the angle, and the derivative of pi x is pi. That's it. Then continue on. Plus your g, which is sine of pi x, times the derivative of x, which is 1. Not much really happens here. You can put some terms together. So let's see. You get x pi times the cosine of pi x plus the sine of pi x. And that's as far as you're going to be able to simplify that. So there is showing you not only product rule, but you can also see a second kind of chain rule. Chain rule with trig. Leave the trig function, or take the derivative of the trig function, leave the angle alone, and then multiply by the derivative of the angle. All right, so how about a classic double chain rule product rule? That's always fun. So here we go. What is the derivative of 2x minus 3 to the 4th times 4x plus 1 to the 5th. All right, so first thing I notice is that you've got one function and a second function that are being multiplied. So you have your f and you have your g. Since they are multiplied, you probably guessed it, that means you're going to have to do the product rule. So fg prime plus gf prime. So this one's not so bad. It looks really ugly, but in the end, it's not going to be too bad. So when you find the derivative here, f prime of x is going to equal, you take your f function, which is 2x minus 3 to the 4th, and you multiply it by the derivative of g. So the derivative of g is going to be 5, so that's chain rule, times 4x plus 1 to the 4th, times the derivative of the inside, which is 4. Plus, then you take your g, which is 4x plus 1 to the 5th, times the derivative of f, which is chain rule as well. It's 4 times 2x minus 3 to the 3rd, times the derivative of the inside, which is 2. You need to simplify each part here. So you see some constants. 5 times 4 gives you 20. So that's 20 times 2x minus 3 to the 4th times 4x plus 1 to the 4th. Then over here, 4 times 2 just gives you 8. So that would be 8 times 4x plus 1 to the 5th times 2x minus 3 to the 3rd. And you are done. So it's not too bad. But that is an example where it's a product rule, but each product rule part has a chain rule involved as well. So where I've noticed most students have a little bit trouble with this idea is what happens when you start mixing quotient rule in. So these next couple examples, please pay attention because they're going to be a little bit more tedious and just a bigger chance of you messing up. So just kind of be careful here. How do we do the derivative of y equals the square root of a fraction of x over x plus 1? Oops, straight mark, my bad. So what we're going to look at here is first, just like any square root, rewrite it. This is actually the same thing as x over x plus 1, all being raised to the 1/2 power. So remember, you're doing the chain rule here. What the chain rule says you do is that even though it's ugly, you bring your power to the front, which is 1/2. Your quote-unquote g of x term is the x over x plus 1, so you don't mess with that. And then you subtract 1 from the power to get negative 1/2. Where you got to be careful is that since this is not just an x, you now have to do the chain rule part, which means you take the derivative of the inside. So remember, your inside, this would be your f, this would be your g, and that's quotient rule because they're being divided. So it's gf prime minus fg prime over g squared. So that would end up being x plus 1 times 1, that's the derivative of f, minus x times another 1, because that's also the derivative of g, over x plus 1 squared. Now I do need you to clean this up, so we're going to go through a few steps here of algebra. So this is going to end up being 1/2 times x over x plus 1 to the negative 1/2 times, you get x plus 1 minus x over x plus 1 squared. And one good thing happens, x minus x goes away. All right, so let's see. This would be the same thing as 1/2. Now, I'm going to split up this fraction being raised to the negative 1/2. You probably remember in algebra that this would be the same thing, is you can apply the exponent to both the top and the bottom. So I'm going to do that and rewrite it as x to the negative 1/2 over x plus 1 to the negative 1/2. The third part I'm not going to mess with just yet. Just leave that as 1 over x plus 1 squared. But as you can see, by breaking it up this way, I now have 3 separate fractions that I can multiply together. Across the top, 1 times x to the negative 1/2 times 1 is x to the negative 1/2. And on the bottom, you have a 2 x plus 1 to the negative 1/2 times x plus 1 squared combines into x plus 1 raised to the 3/2 power. And that's as far as I need you to go. That is an example of where you're doing the chain rule and the inside of your square root or inside of whatever is a fraction and you have to do the quotient rule as part of your chain rule. But it can also be flipped. Here's the switch. On the last one, your chain rule part was the quotient rule. On this one, it's overall a quotient rule, and you'll be doing chain rule inside of your quotient rule, which may sound a lot worse, but actually most people find this one to not be as bad. But I'll let you make that decision when we're done. You've got f of t is t squared minus 1 raised to the third over 2t plus 1 raised to the fifth. So as you can see, once again, this one already has the fraction and there's no square roots to deal with. So I'm going to let the top be f and I'm going to let the bottom be g in this case. All right. So in this case, your quotient rule says that you are going to do gf prime minus fg prime over g squared. So let's take our time through this. We can say that f prime of t is going to equal 2t plus 1 to the fifth. The derivative of f is chain rule, so that's 3 times t squared minus 1 squared times the derivative of the inside is 2t, that's the chain rule part, minus f, which is t squared minus 1 to the third, times the derivative of g is also chain rule, so that would be 5 times 2t plus 1 to the fourth, times the derivative of the inside, which is 2. And then where it becomes not as much fun, you now must take 2t plus 1 to the fifth, which is your g term, and square that whole thing. All right, so in this case, we are now going to simplify this, so a little bit of cleanup work. Let's see, you should get 6t times 2t plus 1 to the fifth times t squared minus 1 squared. And then you get a minus 10 when you put the 5 and the 2 together of t squared minus 1 to the third times 2t plus 1 to the fourth. All of that divided by, and if you have a fifth power raised to a second power, you multiply those together and you get 2t plus 1 to the 10th. Now, what do you notice that everything shares in common? Well, if you look at, let me different color here, we'll do green. If you look at this term, and this term, they all have 2t plus 1s. But how many do they all share in common that you can cancel? Well, the answer is 4. You can cancel all 4 of these off. You can cancel 4 of these off to leave a first, and 4 of these off to leave a 6 to get a more simplified answer, which will end up being 6t times 2t plus 1 times t squared minus 1 squared minus 10 times t squared minus 1 all cubed, all divided by 2t plus 1 to the 6. That is your answer. That is where you have to do the quotient rule, and inside your quotient rule, we had to do the chain rule twice as part of the definition. So make sure you're comfortable looking at both ways the quotient rule can be involved with chain rule. All right. The last little rule we're going to look at here is, and it's not very common, but once in a while you may see it, it's called a double chain rule. And it usually occurs when you have trig functions being raised to powers, so something like this. What if you want to find the derivative of 5 times cosine squared of pi x? Now, what's going to make it a little bit easier for you to recognize this is I would rewrite this the following way. Instead of leaving the squared there, which is more common in practice, why don't we write this as cosine of pi x all squared? They're equivalent, but it's going to be easier to see the double chain rule in this process. So let me show you. When you find f prime of x, you bring the 2 to the front. That's the first chain rule. So 2 times 5 is 10. You leave the inside alone. drop the power down by 1 to the first, and chain rule also says you must take the derivative of the inside. Well, the derivative of cosine is negative sine, but now you notice that your angle is not just x, it's pi x. So that means when you take the derivative of cosine pi x, the cosine is negative sine, and then you have to multiply by the derivative of the angle, which is also pi. That's it. So you had your chain rule part here, and then you had the part right here that you left alone. So those are both considered chain rules. If you put together your terms, let's see, there's a negative, a 10, and a pi floating around, and then you have the cosine of pi x times the sine of pi x. That is an example of a double chain rule that you may see. Not very often, but once in a while, there it is. All right, and to wrap up this video, we haven't done a tangent line for chain rule, so let me show you an example of where you can find the equation of the tangent line to the curve, and let's do, why not, y equals sine of sine x, and I want you to do the tangent line at the point pi 0. And while you may be thinking, oh, this is a double chain rule as well, actually it's not. It just looks a little bit weird, and it gives the misconception that it actually is a double chain rule. So once again, as we've learned all during this video, to do tangent lines, first thing you want to do is you want to find the derivative. So in this case, you have to treat this second sine of x as kind of like your theta. So the derivative of sine, the outside one, is cosine. You leave the inside alone, which is sine of x, but then you have to multiply by the derivative of this theta. So the derivative of sine does give you another cosine of x. That's it. That is your derivative. Step number 2, to find the slope of the tangent line, you have to plug your x value in, which is going to be pi. So that's going to end up being the cosine of the sine of pi times the cosine of pi, and you have to know your trig values here. This is the cosine of sine of pi is 0. The cosine of pi on the outside is -1, but then you pick up another trig function. Cosine of 0 is 1, so 1 times -1 gives you a slope of -1. Now that you know the slope and the point, you can write the equation of your line. This would be y minus 0 equals -1 times x minus pi. Well, the y minus 0 just becomes a y, the 0 goes away, and if you distribute that negative through, you have a tangent line of the form y equals -x plus pi. So there's a way that you can also do tangent line of chain rule. So in this video, we went over all of the rules: the power rule, the product rule, the quotient rule, trig derivatives, and the chain rule. Those are very important going forward after your midterm exam. We also talked about how to do tangent lines in general, and we also talked about horizontal tangent lines in this video. So make sure you go through and look over all these derivative rules because they will be necessary in future sections after the midterm.